Okay, so in the last class, we learned about the telegrapher equations, and these telegrapher equations are the equations that are used to represent the relationship between the voltages and the currents in a transmission line, right? So these telegrapher equations were first introduced by a scientist called Oliver Heaviside, and these scientists uh, derive these equations, model these equations to analyze or study the transmission lines and the voltages and currents in the transmission lines that carry the telegrapher messages uh, from one point to another point, right? So they had telegrapher transmission lines at that time. So telegraphs were the messaging system they had at that time. So they wanted to deliver the messages reliably from one end to the other end. So they wanted these scientists to model how the voltages and currents behave in the transmission line. So by modeling these kind of equations, the engineers can identify like how the voltages and currents behave and how the voltages and currents attenuate from one end to the other end. Once they know that, they can either amplify the signal or the wave at the point where the attenuation is very high, and then they can improve the energy of the wave that is transmitted, and they can make sure, or they can increase the reliability of the communication system, right? So we assumed of a case where we are assuming that the series resistance and the parallel resistance is almost zero, right? That means that in our transmission lines, there could be a situation where our resistance in our transmission line is almost zero. That means our resistance is zero, means the lines that we are using are very highly conducting wires. And then also that the dielectric medium that we are using between the two conductors of the transmission line is almost a perfect dielectric. That means the stray currents that flow from the top conductor to the bottom conductor is almost zero, right? So the stray current is almost zero. So dielectric medium is almost perfect. So in that case, we can assume that R is equal to 0 and G is equal to 0, right? In the circuit diagram that we considered, we can so in the circuit diagram we considered, so in here we have the R. Where is this? Okay. Right, so the R, the resistor, and the parallel resistor, we have these two components. So in lossless transmission lines, these components, we assume that they are equal to 0, right? Because the conducting wire is a very good conducting wire, and therefore the resistance is almost negligible, right? When we consider with the inductance that is generated because of the current that is flowing in the transmission line, the resistance value is almost negligible. And also when we consider the capacitance or the voltage that is formed between the two conductors because of the voltage difference between the two conductors, that capacitance value is higher than the parallel resistance value that is generated here. So because of that, we assume that the G value or the conductance is 0. Right? So in that case, we are assuming that the dielectric also is almost perfect. So because of that, the stray currents, the ability for the material to conduct stray currents is almost 0. And then, we consider the lossless case, and the lossless transmission line can be here, can be the lossless transmission line and its properties can be applied to the telegrapher equations that we studied earlier. So once we substitute those r equals 0 and g equals 0, these terms will be 0. Right? We are only left with the minus L into double I over double T. And for the current equation, we are left with only the minus C into double V over double T. So, we are left with these two equations once we substitute R equals 0 and G equals 0. So after this, we can now actually get more relationships between the currents and the voltages. Right? The first relationship we can take is about voltage only. Right? We take only voltage, and then we see the performance of voltage behavior. So once we get the equation, we can see that the voltage is behaving with respect to the position and with respect to time in this relationship. And then we can show by the laws of physics that the voltage is behaving as a wave in this transmission line scenario. Right? Because of that, we can equate the classical wave equation in the physics to the wave equation that we get in our transmission lines. Right? So in the transmission lines, this LC component gives the constant in the wave equation. So in the physics wave equation, the constant is given by 1 over velocity of the wave. Right? The Vp is the velocity of the wave. And we can equate these two constants and form another relationship between the velocity of the wave and the LC parameters of the transmission line. So the wave velocity will be equal to 1 over square root LC in transmission lines. So in lossless transmission lines, we can directly use the value of L and C to find out the velocity of the wave propagating. Right? Then we come to the new content, which is like the solution for the equation that we have got using our previous derivations. And the solution for this type of a voltage wave equation is in the form of this expression. And so there are two terms in this expression, which is the first term is the forward voltage wave. Second one is the backward voltage wave, right? Right. So this comes from mathematics, right? That if there's a equation like this that shows that the voltage is in this behavior, then the solution for that equation should be of this manner. Like it should be a superposition of two voltages or superposition of forward and backward waves, right? Backward signals, voltage waves. Okay, so the general solution for this type of equation is mathematically the superposition of a forward going voltage and a backward going voltage, right? So for the same, similarly, we can get for current also, the current at one location in the transmission line is equal to the addition of the voltages going forward and the voltage coming backward, right? So we will talk about the forward going voltage and backward going voltage, right? So in order for us to simplify our equations further, we use the phasor domain representation of the voltage wave, right? The phasor domain representation of the voltage wave we can give using this in this manner, right? So if we have a V, so in phasor domain, we denote our parameters in capital letters. So voltage, we denote the phasor domain representation of the voltage, we denote with capital or uppercase letters, and we denote the voltage as the magnitude of the voltage at a certain location Z into the exponential of the angle or the phase shift of the wave, right? So omega t gives the angle of the wave that is propagating. So it gives us the phase shift of the wave, right? So once we take the voltage in this phasor domain, and once we take the derivative of that expression with respect to delta t, then we can actually we can see that once we take the derivative of the voltage wave with respect to the time, since the derivative of a exponential function is itself, and the additional part is coming from the additional components apart from the variable, so this is going to be equal to Vz, right? The same expression into j omega, right? J omega into Vz, and Ej omega is t, right? So once we take the derivative of the voltage wave, we can take that it is equal to j omega into the same expression, original expression, right? So only the additional component is j omega. I hope it is clear to you. So if you can't understand this derivation, please let me know in the chat. I will answer your questions. So, right. So this is just a mathematical computation. You take the derivative of the voltage wave with respect to time. And once you take with respect to time, then you are left with the original expression plus the j omega term, right? So because of that, now we can say, right, since these two terms are similar, we can, these terms are similar, only the j omega term is remaining. Therefore, in mathematics, we can derive the relationship that j omega can be equated to W over W t, right? And then by using this relationship, right, we can simplify our equations further. Right? The telegrapher equations we have are given in these first two equations, right? So once we take these equations, we have in those equations these terms like W I over W t, W V over W t. So these expressions can be replaced by j omega term. So by replacing by j omega term, we can simplify the equations in this manner, right? Apart from that, you can see that Vzt is replaced by Vz only in here. So in this case, we are considering that time is, we are not considering the voltage with respect to time, but only with respect to Z, right? So the reason is that we are not considering variations in time at this, in this calculation. We are considering only the variation of the voltage with respect to the position in the transmission line. So we are considering the other variable and its variation on the voltage negligible or it's fixed, and we are considering only the voltage difference that happens at each location of the transmission line. So we are considering a unit time instance, and at that time instance, how the voltage is behaving at each location of the transmission line, right? So at different locations of the transmission line, the voltage is changed because the voltage is moving as a wave in the transmission line. So because of that, the voltage magnitude is not the same at each point in the transmission line. So once you measure the voltage and the current in the transmission line, you can see different magnitude or the variation in magnitude or the voltages and currents along the transmission line. Right? So then you can obtain these equations once you substitute, instead of VZT, you substitute VZ, right? You take VZ and then you substitute J omega instead of dabba I over dabba T. And then similarly for the current, you can do the same thing and you can obtain this equation with respect to current IZ and J omega VZ. Right? So in here also IZT is replaced by IZ and VZT is replaced by VZ. Right? By writing like this, now the equations look very simpler and very clear and very easy to understand. And then we can since we can see that there's IZ on both in both terms, we can take R plus J omega L into one term and we can write like this. And similarly for the second equation, you can take VZ term outside and then you can group the G plus J omega C term into one term within the bracket. So likewise, we can do all those simplifications and then we can now take the derivative of the equation that we have with respect to the voltage on both sides by dz. We take the derivative with respect to z on both sides and then we take the derivative, I mean the second derivative of the voltage with respect to position, and then it will be equal to this expression R plus J omega L into d Iz over dz. Similarly, we can use the previous equation that we got for diz over dz, which is this equation, and we can substitute that in here. Right now, we are trying to find again the relationship between the voltage and we want to remove the IZ term. So in order to remove the IZ term, we are going to substitute this equation and the term for diz over dz over to this first equation. And by doing that, we can get this expression for the voltage relationship. So the voltage relationship will look like this, where this expression that we have with regard to the R plus J omega L term and G plus J omega C term, we can take those constants, or actually omega is not a constant. However, these parameters define the transmission line behavior. So these parameters are denoted using a constant known as the propagation constant, right? So this parameter is necessary for us to understand how much the wave is propagating and how much of a phase shift is there for the wave, or how much of phase shift is there of the wave per unit length. Right? Those parameters are defined by this propagation constant. And the propagation constant is defined by this R plus J omega L into G plus J omega C. Right? So similar for the V voltage equations, we get the same relationship for the current parameter in the transmission line, and we can show that current also show the same relationship with respect to like right, with respect to the taskbar setting. I will just hide this taskbar so that I don't know how to hide it. Right, so we can get the similar right, so we can get similar relationship for the current with respect to we can get the second derivative of current and we can relate it to the current parameter, and the constant here will be gamma squared, the same constant that we get for the voltage. Then we have the definition of the gamma in terms of parameters alpha and beta, and we define the alpha parameter as the attenuation constant, and we define the beta as the phase constant. This is known as the attenuation constant, and the beta is known as the phase constant. So the gamma, which is defined as the propagation constant, can be represented as a complex number, right? So it has the real part and the imaginary part. The real part is given by the attenuation constant. The complex part is given as the phase constant. It's defined as the phase constant. So it is also represented using R plus j omega L and G plus j omega C square root. Right, so that is all about the gamma parameter. So earlier we got this equation related to the second derivative of the voltage with respect to the position, and we got this equation, right? So the solution for this kind of equation is in this form, right? So this I discussed in previous lecture slides also. Right, the solution for such a equation will be in this format, I said, right? So the solution for this kind of a equation will be in this format, right? However, we got this for the time with respect to time and all, right? But now, since we are going for the simpler notations using phasor notations, we are now writing it in this manner. Right? Same expressions, but we are writing in the phasor domain, right? So this is a like we are taking the voltage with respect to Z variation only, right? So we are considering the Z the voltage variation per um, uh, per each location, and we are assuming that we are considering one time instance. So for that case, we again have the solution for the voltage as the forward going voltage and the backward going voltage, right? Forward voltage and backward voltage, right? The forward voltage magnitude is denoted by V plus naught, and the backward going voltage magnitude is denoted by V minus naught. And then the forward voltage's exponential term has this minus sign in order to show that it is going in the forward direction, right? Then we have in here the exponential to the plus RZ to show that the wave is going in the opposite direction or in the minus direction. So for example, we take a transmission line, right? We have like a transmission line, and then we have our voltage wave going like this at a certain location, and then at the same location we also have the the backward going voltage also, right? The backward going voltage has the magnitude of V naught minus. This forward going voltage has a magnitude of V naught plus, and this voltage magnitude and its phase is given by minus is R Z, right? This one, for this one, it is given by E R Z. So this is how we can represent mathematically the forward going voltage with the with this kind of e to the minus gamma Z, and backward going voltage by e to the plus gamma Z, right? So that comes with the understanding about the signals and how they shift forward and how they shift backwards, right? Same scenario is considered for the current as well, and we can denote the current out of this equation. The solution out of this equation we take as current equals to the forward going current and the backward current. right? So the superposition of those two current waves give us the total or the average current at a certain location Z in the transmission line. So I hope that is clear to you. If you have any questions, you can ask. And then we have other things which are about the characteristic impedance of the line. Okay, characteristic impedance gives us an intuition about uh, the ability for the transmission line to transfer energy from one point to another, right? Ability to transfer energy in the transmission line, right? So if the impedance is high, that means the ability of for transmission of energy is low. And then if the impedance is low, that means the ability to transfer energy is high, right? And then so we can determine this characteristic impedance by taking the ratio between the voltages and the currents at a certain location, at a certain general location in the transmission line. So the general voltage in the transmission line we can denote as this expression. But in here we have considered a case where we only have a forward going voltage, right? When we assume that we only have a transmission line where the transmission line is having only the voltage supply and the waves are going up to infinity and it is not getting connected to any other load or any other component at the end of the line. So at that case, we only have the forward going voltage, and in that case, we are only left with the forward going voltage component of the voltage. So we can define the voltage at that at any point in the transmission line in that case using this expression. Then current also we can consider the only the forward going term, and we can define like this. Then we need to take the ratio between these two terms in order to find out the characteristic impedance of the line, right? So the characteristic impedance of the line we will see later. It is defined basically on the characteristic of the transmission line. That means the L and the C and the R and the G of the line. So it depends on the parameters or the fixed parameter or the inherent characteristic or inherent parameters of the transmission line. So the resistance, the capacitance, the inductance, the conductance of the line, right? So the characteristic impedance depends on those parameters. And then uh, we can take in order for us to take the such kind of a relationship, we need to remove these unknown terms that we have. We need to remove terms like V naught plus, I naught plus, and so on. So in order for us to do it, we are taking again the telegraph equations that we built earlier with respect to the propagation constant. And then we substitute we can take the derivative of this equation with respect to dz, right? Derivative with respect to z, and then we can obtain this equation, right? I hope it is clear to you. We take the derivative of this with respect to z and we compute dv over dz, right? Then we can write that it is equal to minus gamma into Vz, because this term is again equal to Vz, right? And then from the telegraph equations, we know this one, this relationship we know from the telegraph equations. And then since these two are equal, right, we can equate these two expressions, right? So by equating those two expressions, we can get this expression where Vz over Iz is equal to R plus j omega L over gamma. And by solving these two, and by substituting that gamma is the square root of R plus j omega L into G plus j omega C, we can obtain the relationship that the Z naught is equal to the square root of R plus j omega L divided by G plus J omega C. And then we also denote like in with respect to the voltages and currents, we denote the Z naught as the ratio between the forward going voltage and the backward forward going current, right? So likewise we can denote the characteristic impedance with respect to the voltages and currents and the parameters of the line, which are R, J, R, C, G, and L. Right, so we have these equations. So similarly, we can consider backward going voltage as well, and then we can use the backward going voltage, and we can take the ratio between the backward going voltage and backward going current, and we can take the expression for Z naught using our equations and in the similar manner, and we can derive that the Z naught is equal to the minus of the V naught minus and I naught minus. So V naught minus denote the backward going voltage. We take the minus sign because the current is now going in the backward direction, right? So I naught minus denote only the magnitude of the backward going voltage, but in order to represent that this is a backward going voltage, we are adding the minus sign in front of the this V naught over I naught ratio, right? So we can denote Z naught as minus V naught minus divided by I naught minus, right? So apart from that, in this scenario, there is a difference than the previous scenario. Now we have the backward going voltage, which is going up to the infinity towards the power source, right, from the load, right? So now, like previously, we considered the case where we had the source, and from that source, then we are transmitting a voltage wave and current wave from the source end towards the load end side, but it is a never ending transmission line. So there's no load connected at the end. The forward going voltage is going up to infinity, right? That is a consideration we had in this scenario. That is the scenario we considered here. So now we are considering the scenario where our backward going voltage is going up to the infinity and in the direction of the power supply, right? So from the load end up to the infinity side towards the side of the power source, the wave is traveling in this case. And in that case, we don't have a forward going voltage. We only have the backward going voltage. The backward going voltage is represented by V naught minus E gamma Z, right? So that is the backward going voltage. And then I think we derive that in our this expression, right? So this is the backward going voltage, right? And this is the backward going current, right? So we, in this scenario, we have backward going voltage and backward going current. So in that case, we need to take the ratio between those two components to find the impedance of the backward going voltage wave and the impedance related to that wave propagation. And we have in this scenario, the expressions we have are like this. So we can take the V naught minus ER gamma Z and I naught minus E gamma Z as the backward going voltage and the backward going current. Then we take then we try to um, simplify this more further, and we are trying to remove the components which are related to I naught minus and V naught minus. Those parameters we are trying to replace by gamma, right? So gamma is a constant which gives us the relationship between gamma and the R plus R, L and G and C of the transmission line circuit. So in order for us to get those known parameters into this equation, we are again we are again trying to simplify these two equations. We are taking the derivative of the first equation with respect to z, and then we are obtaining this equation. And then secondly, we use the telegraph equations again, and then we use that equation to get the dv over dz relationship. Right. In this case also we can take the ratio between the voltage and the current. So since it is a backward going voltage, the minus sign should be staying in this side uh, of the equation, right? Because IZ is just denoting the magnitude of the current going in the backward direction. It is not giving us the direction of its movement. Since this is a backward going voltage, it is necessary for us to mention the minus sign in order to show the backward direction of the wave propagation. So since we are considering backward propagation, we need to include the minus sign in this side of the equation. So once we take the minus sign into this side, we can obtain this expression as the Vz over minus Iz expression. So Vz over minus Iz is equal to the Z naught in the Z naught, and we can take the same expression as we got earlier for the uh, characteristic impedance in the forward going voltage scenario, right? So in both forward going voltage scenario and backward going voltage scenario, the characteristic impedance is same, and it is equal to R plus j omega L over G plus j omega C, right? The way it is denoted using voltages and currents are different, where the forward going voltage and forward going current ratio is equal to Z naught, and the minus of the backward going voltage and the backward going current, the ratio between those two components is equal to the characteristic impedance, right? So after that, so we have obtained those equations for the characteristic impedance. So now we know like what is the impedance of a circuit of a transmission line to propagate a certain wave, uh, propagate a certain wave from one point to another point, right? So the transmission lines, right, depending on the type of the transmission line, the propagation can either be we can consider propagation can either be like attenuation free or attenuation incorporated, right? So that means that once we are considering transmission lines, we need to consider that the wave that is propagating in the line has will get attenuated, or due to some constraints in the transmission line, imperfections in the transmission line, or any other environmental parameters. And in that case, the magnitude of the voltage and current waves will vary with the transmission line, with the position in the transmission line, right? So in that case, we need to consider two types of transmission lines, right? So we need to consider about the lossless transmission lines and the lossy transmission lines. So I mentioned about the lossless transmission lines earlier as well. So in that case, in the lossless transmission lines, we have assumed earlier that the resistance is zero and the conductance is zero. Apart from that, the attenuation constant that is appearing in the propagation constant, we have it equal to alpha plus j beta. So in that expression, alpha will be equal to zero for the lossless transmission line case, right? So in this scenario, we have alpha equals 0, r equals 0, g equals 0, right? So in most of microwave communication, like engineering designs and related studies, we consider lossless transmission lines in most cases, sometimes because we have very highly conducting wires. That means r is equal to 0, and then we have like good dielectrics. So because of that, we can make g equals 0. At that moment, the attenuation of the wave is also kind of negligible. So we take that alpha is equal to 0. right? So when we are doing the calculations in transmission lines and in other components, we sometimes take into consideration that the transmission line that we are using is lossless, right? So depending on the condition we have and the materials we have for the transmission line. So and then we have the second type of transmission lines, which we call as lossy transmission lines. So in that case, we have the alpha parameter not equal to 0. That means some value is there for alpha parameter, which is above 0. And that means that the wave that is propagating will be attenuated as it moves along the line. So with the position in the transmission line, the amplitude of the voltage and current waves will decrease with the time and the position. So therefore, it is important for us to know like some parameters related to lossless transmission lines. And in order for us to use these uh, characteristics in our different propagation scenarios in the transmission lines. So we have in the lossless transmission line, we have the resistance equal to 0, as I said before, then G equals 0. And then at that moment, we learned about the characteristic impedance, right? So the characteristic impedance is one of the very important parameters in the transmission line. So characteristic impedance is used to denote how much of a resistance is there from the transmission line to transfer energy from one place to another place. So it is given by just the square root of L over C in the case of lossless transmission lines, right? So otherwise, if we don't have the lossless transmission line, this is going to be equal to Z naught equal to R plus J omega L divided by G plus J omega C. However, in the lossless case, it is simplified and only the L over C term is remaining inside the square root. So therefore, it is much more simpler when we consider lossless transmission lines in our calculations. Then also another very good advantage of lossless transmission line is that voltage and current waves are in phase. There's no phase difference between the voltage and current waves in the lossless transmission line cases. So because of that, maximum energy is transferred from the transmission line to a certain load or a certain impedance or some kind of a component, right? So we are having this voltage and current in phase in lossless transmission lines. And then we have the propagation constant. The propagation constant, I mentioned that it is given by gamma, and it is normally equal to alpha plus j beta, right? So in lossless transmission lines, the alpha component is 0 and only the j beta component is remaining. Because the attenuation is 0 in lossless transmission lines, and therefore the attenuation will be 0. Attenuation constant will be 0. And then also we have the beta component, which we call as the phase constant. Phase constant will be equal to gamma square root LC, and it is denoting like how much of a phase shift is happening per unit length, right? Per unit length, right? When the wave is propagating. So it is denoted by 2 phi over lambda, right? And then we have wave velocity. That means at which velocity the wave is propagating along the line. So we derived this expression in our last class also, which is 1 over square root of LC, right? So when we consider lossless transmission lines, we can denote the wave velocity by using only L and C components of the transmission line circuit. And then we have the wavelength. Wavelength we can define using beta, because in beta we define beta as 2 phi over lambda. So by taking lambda as the subject of that equation, we can denote that lambda is equal to 2 phi over beta, and which is again we can denote as this equation by substituting omega square root LC for the beta expression, and we can get this term for the wavelength. Also, in most high frequency transmissions, as I said before, we have the resistance very negligible when we compare with the inductance caused by the currents going across the transmission line. And then we have the conductance very small and negligible compared to the capacitance that is created across the transmission line. So because of these reasons, we can do the assumption that R is equal to 0, G is equal to 0. Likewise, the same assumptions we can make as the lossless case for the high frequency wave transmission case, because at that case, we have this relationship of resistance being negligible compared to inductance and capacitance. And then we have like the importance of characteristic impedance, right? So why the characteristic impedance is important, right? For efficient maximum transfer for to occur, the characteristic impedance must match the impedance of the load, right? That is very important uh, idea that we need to have in our minds when we are designing microwave systems, right? So there's a certain characteristic impedance of a transmission line, right? So we know that the ratio between the voltage and the current, right? When we take the backward going voltage and backward going current, the ratio between them, and the forward going voltage and forward going current, the ratio between them will equal to the characteristic impedance of the transmission line. And this characteristic impedance is denoted by Z naught. And once we have a Z naught in here, we connect our transmission line to a certain load. Let's say this is an antenna, right? So the antenna is having some impedance, and its impedance is ZL, let's say, right? So the Z naught and ZL, they could be different values, right? If the values of these ZL and Z naught are different, maximum transfer from the transmission line to the load does not happen, right? So I think even in circuit theory, you must have learned this, that once the impedance of a circuit, once you are having a certain voltage supply and you are having some kind of a impedance, and then you are supplying some voltage across another impedance, then once we have the same like resistor or impedance at both the locations, we can transfer maximum power across the Z1 impedance, right? We need to have these two impedance same in order for us to transfer the maximum energy from this input circuit to the load circuit, right? So in order for that to happen, we need to make sure that, or we need to design our system such that Z naught is almost equal to 0. Z naught is almost equal to ZL, and that these two impedances are equal or matched, right? So in order for us to uh, match those like impedances, we have different techniques for impedance matching and so on. So in order for us to uh, get an idea about how much of the wave is getting reflected back, we need to find some more parameters regarding this transmission line. Right? So in order for us to find a parameter called reflection coefficient, we need to first find we need to find a very simple equation for that, right? So in order for us to get a relationship between the Z naught value and the ZL or the load impedance value, we need to take the ratio between the voltages and currents at the load end, and we can obtain a expression between the ZL and Z naught at the load end, and using that we can obtain a simplified equation for the reflection coefficient of the line. right? So we will learn about the reflection coefficient, which is given by the tau L in the upcoming class, right? So tau L gives us how much of a voltage is getting reflected back once we feed a certain voltage value to the load, right? So the tau at the load will be given by how much of voltage we supply to the load and how much of voltage will be reflected back from the load towards the power source N. So that we will continue from the next class. So I will stop the class now.